We have an example problem here. A series RLC circuit has a 50 Hertz AC source, an 85 ohm resistor, a 0.5 Henry inductor, and a 35 microfarad capacitor. The RMS current in the circuit is 3.1 amps. So two questions. A, what is the RMS voltage of the source? And B, what is the average power dissipated by the resistor? All right, so our source voltage connected to a resistor, an inductor, and a capacitor. We don't necessarily need to draw the picture per se. We do need to know they are in series though. L, our inductor, is 0.5 Henries. C, 35 microfarads. And it tells us the RMS current in this circuit is 3.1 amps. So in an RLC circuit, in series specifically, we have the current in this series circuit is the source voltage over Z. Now it's written in terms of max values, but we've seen in previous videos, if we divide both sides by the square root of 2, this max over square root of 2 is the RMS value of the current in the circuit, and then the maximum source voltage over the square root of 2 is the RMS voltage. So we can use the same relationship as long as both current and voltage are RMS. In this particular case, we're given, we want the ERMS, the source voltage, which means we need to figure out what Z is, the impedance, which totally can do. We're given the frequency of 50 Hertz in an RLC circuit. In series specifically, Z is the square root of R squared plus the quantity of XL minus XC squared. Now, I personally like to find XL and XC individually because it's really easy to miscompute XC in particular. So XL we know is omega L. Omega is 2 pi f. We've been given f of 50 Hertz, so 2 pi times 50 Hertz times the value of the inductor is going to give us XL. So 2 pi 50 times 0.5, 157.08 ohms. XC is 1 over omega C. I think the reason this one's most commonly miscalculated is we forget to put the parentheses around the whole denominator. We know omega is 2 pi f, and f is 50 Hertz. Now we need to multiply by our capacitance, which is 35 micro. So just make sure you have parentheses around that whole denominator. Oh, 2 pi f times 35. Okay, I'm getting 90.9457 ohms. So plugging this in to Z, R is the value of the resistor. Plus XL 157.08 minus XC 457. That quantity needs to be squared. So Z current squared plus quantity minus that. I'm getting 107.7 ohms. It's 0.697, so I'm just going to round to the 0.7. Z, the impedance, represents the overall ohms in the circuit. So kind of an equivalent resistance of sorts. Not exactly the same thing, but it does directly relate to how much current can flow. So coming back to this left side, where we were talking about the source voltage, we're given the RMS current that is flowing. We just calculated Z, the overall impedance. So the source voltage, I'm getting 334, but we only have 2 sig figs, so approximately 330 volts RMS would be this source that results in this specific RMS current when the frequency is 50 hertz. By the way, if we were to change the frequency, that would totally change Z, which would in turn means the source voltage was different. Or if the source voltage is fixed in terms of the actual volts, and we change the frequency, that would change how much current could flow. Z always changes with frequency, and that's because XL and XC depend upon that frequency. So part B, we want the average power dissipated by the resistor. I tend to like just I squared R, where I is specifically the RMS current, which we've been given. R is the ohms, the actual resistor value. So 817 or approximately 820 watts would be the power dissipated by this resistor. So hopefully going through these different example problems is helping you to see how to put these equations together. We do have one more concept we're going to talk about as well.